introductory talk, so it should be accessible to students, especially masters and beginning year like PhD or even final year undergraduate. um, so this topic has interest in many problems of calculus of variations. Um, the kind of problem which the talk relates to is you're interested in general uh, minimizing a function which is defined on a family of domains. So omega, this O script O AD is the admissible class of domains. Maybe the class of open sets with some smooth boundary, or maybe open sets with Lipschitz boundary, or sometimes more irregular kind of sets. uh, And the typical question one wants to study is that given this function, which is a function of the domain, you want to minimize the function in this class. Can you do it? Can you find existence to the problem? And if you have solution, can you characterize or calculate the solution? More or less, this is the question. And so to put it in context, uh, we can talk about two typical problems. One is if you look at j of omega, um, you may take the j function to be the area of a planar domain. Omega is a domain in the plane. I can draw figures, but to switch will be difficult. So uh, so this is omega, and when you change omega, you get different shapes, maybe rectangle, maybe some other smooth domain, whatever. So for each of these domains, all you need is the area to be defined, which means it should be bounded by some curve whose area you can calculate. So to calculate area, you don't need much regularity. You just need the Lebesgue integral to exist. But if you want to restrict the class of domains which have finite boundary, then the boundary has to be smooth enough. Maybe at least like Lipschitz boundary to be able to talk about the length of the boundary, the perimeter. So the the typical or classical problem of isoperimetric inequality is among all domains of given perimeter, the perimeter is fixed. For which domain the area is maximized. The problem of minimizing area doesn't have much sense, because if you fix the perimeter, you can take arbitrarily long rectangles with small thickness, satisfying the length condition, and of course, it cannot be arbitrarily long. Meaning, the sum has to be, but you can see that the area goes to zero when you have the thickness going to zero. So if you take half the length minus epsilon, and this will be epsilon over 2, then the area is of the order epsilon, and the perimeter is L, right? This should be epsilon half also. Okay. If you want the sum to be L, the perimeter to be L. So it doesn't make much sense to talk, or it is not interesting to talk about minimizing. The interesting problem is maximizing the area. And the solution to this problem is well known from olden times, and actually it appears in the book of Aeneid uh, by Homer. So he talks about the Queen Dido, or Dido, I don't know how to pronounce, from Tunisia. She was exiled from her country, and she reached a place with her group of people. Uh, And the local tribal leader said, I can give you some land, but all that land you can cover with a piece of leather, which he gave to her. And then she was clever, and then she cut the leather into long strips, very thin strips, and then decided to. So she was near a river, and so she covered like this way, and even though the area of the leather piece of leather was small in the beginning, by cutting into thin strips, you can have infinitely, arbitrarily long perimeter, and so she was able to get a big area covered by the perimeter. And the form of the city she founded was a semicircle in this case. It's mythology. Probably it's not so historic, but to say that even in those times people had an idea. And if you look at modern cities which are on the river side, or even cities like central cities like Paris, so they expand in more or less in a uniform way, and the more or less the outer circle of the city is more or less a circular form. So
you save money in building walls for defense.
Yeah. Exactly. So in olden times, if you had to protect the frontier, then it's easier to protect by having a circular shape. And also it's probably a good form if you want to get to the center as soon as possible, if people need to go to the center to work or something. So people who live on the outskirts, they are not at a disadvantage if you have a different shape. So some people may have advantage and others no, if you have a different shape. So it may work for many reasons. And then a more modern problem was conjectured by Lord Rayleigh. He was just a scientist in those times, I think, could not classify them exactly as mathematician or physicist or philosopher. But he has a treatise called the Theory of Sound. In this, he asked like 3 questions which are of some mathematical interest. And the question is, given a drum of some shape, so the drum is fixed on the boundary. So the drum is fixed on the boundary, and so when you excite the drum, it has some modes of vibration, and the lowest frequency is the base frequency. So it's the lowest eigenvalue for the corresponding problem, which is a Dirichlet equation. So minus Laplacian u equals lambda u in the domain, and u has to be 0 on the boundary, because the boundary in this case, on the boundary, there is no vibration. The drum is fixed on the boundary. And so the lowest frequency, there are many vibrating modes. So you take the lowest for this shape, and it will change with the form. When you take a different shape of the drum, it has a different lowest frequency. And the question he asked, or the conjecture he made, was that this has to be the least when the drum is the shape of a circle or a disc. And this, although this conjecture was made in 1870 something in his book, to get a solution was like 50 years later by 2 German mathematicians, I guess. Independently, they proved the conjecture. So it's just to give you an idea that the problems of minimizing some function which depend on shape can be interesting, natural, for different reasons. And more, if you want like more motivation, then one has to look at engineering problems where you want to have the best aerodynamic shape of some wing, or hydrodynamic shape of a shape or hull. So many of the problems can be formulated as shape optimization problem. And also many shape optimization problems can relate to problems of imaging or inverse imaging. So if you want to identify some hidden object inside a body, for example, a tumor inside the uh, head, if you have a brain tumor, you cannot go and do surgery, and so you use X-rays to get some idea of the sections, but those do not tell you exactly. They are like you're measuring information on the boundary you for some physical situation. So using this information, can you say if there is a hidden object or not? So if there is no hidden object, then the X-ray would have passed in a certain way. But since there is a hidden object, the data which you receive is different. And so uh, seeing the differences in the data, you want to say whether what kind of shape is there. So you can initially suppose that the shape has some size or some mass, and then you do not know the shape, but you want to locate where this shape is. So then you need to again formulate some functional, because it will measure the error whether when there is no obstacle versus when there is a error when while versus where there is a obstacle. And so by minimizing a suitable functional like this, you will be able to approximately say what is the size shape of this obstacle. But this is a difficult problem, and I think I'm not so expert in this, and I think I mean, even as I speak, I think there are people who are working on better ways to identify obstacles in many different situations. So these are typical inverse problems. So given this motivation, I will go back to something more basic. So as I said, the existence of a shape which minimizes the problem, and to identify the shape are the two main problems of interest. Since I have prepared as a beamer, the same questions repeat on different slides. So, okay. So what tools do we have to study these problems? So I want to talk about the tool which is being used in some time, and I think this tool at least has a history of maybe 100 or 200 years. It's not new, but it's frequently used nowadays for studying this kind of problem. So just to uh, say to compare with what we do when we have a finite dimensional minimization problem, or even infinite dimensional minimization problem, where the object of study is not a shape, but these can be represented as points in some Euclidean or normed space. Okay, where there is a vector space structure. So if you have a vector space structure like the real line, if you have a function which is a smooth function, at least one times differentiable on an interval, of course the function is continuous, and we know it will have a maximum and minimum in the interval if it's a finite interval and closed. And then you can you know from calculus that there are first order necessary conditions for a local minimum or local maximum. the first order condition says that the derivative of the function in a possible maximum or minimum has to be 0 if it's not on the boundary, an interior maximum. And if it's 2 times differentiable, then you can say that if the Hessian, the second derivative, is positive, then it has a local minimum. If it is negative, then it has a local maximum. So these are well-known facts, and the same can be said even in infinite dimensional normed space, where you can talk about the same idea of derivative, but you need to talk about Frechet and Gateau derivative. The derivative has to be thought of as a linear functional on the space. The derivative at a point is a local approximation. It's an affine approximation of the function. So the affine approximation is given by linear functional at the point, right? So the d of x0 in this case will be the linear or affine approximation of the function in this point. So what I mean to say is that if you have a infinite dimensional space, you can think of the derivative at a point as a functional such that f of x is approximately given by f of x0 plus
right above because
yeah. So f is a function on some normed space. So f is Frechet differentiable at x0 if f is approximately equal to f of x0 plus L x minus x0, where in a neighborhood of x0, which means where L is a linear functional from the space to the space of let's say we are talking about real valued function because we are talking about minimum maximum. So L at this point, so it's an affine approximation of f, and L is the linear part of the function, right? So for a maximum or minimum, you can again check that the linear functional here has to be 0, a necessary condition. And if you want to look at sufficient condition, then you have to look at higher order derivatives, again in the same sense. So if this exists, then x which goes to L of x at every point is another function. This may be again a nonlinear function. And so if this is differentiable, then the derivative of L, which we denote by dl, will be so the values here are in the space of functionals. So it will be from in the double, so the L belongs to the dual space and dl will belong to the double dual. It's a linear functional on the linear functionals, right? Which means it's like a bilinear form on x cross. If x is a Euclidean space, then you can think of it as a bilinear form on x. Okay. So and then so in the case of an inner product space, then you can think of it as a bilinear form. And if this bilinear form is a positive definite form, then you have a local minimum, and if it's a negative definite form, then you have a local maximum. So this is the equivalent of the necessary sufficient condition for Euclidean space in a Hilbert space. Okay, for a function which is defined on some normed space. Okay, I don't know. For example, what should I give? Like an example here. I think f of x, if it itself like a quadratic form, like the norm of x, the distance from a fixed point, given point in the space. So x is lives in a Hilbert space or in some Euclidean space. So this is the distance from this. Then the linearization will just be at any x will be x minus a, in the sense that this will act on 2 times, or let me put half. So this will be x minus a. So, and the second derivative in this case is the identity matrix. Okay. So this will be a minimum when df is 0, which tells you that it's minimum when x equals a, which is obvious because you are trying to minimize the distance to a, and the identity matrix is a positive definite matrix because the eigenvalues are all 1, and therefore you have a minimum. So just to put in context what is the usual procedure, but how to do something like that in the case of functions which are defined on whose points are sets. These points are no longer in a vector space or a normed space. So you need some idea how to perturb the domains and how to calculate perturbations of the functional with respect to perturbation of the domain. Okay, so this is the main idea. So I don't know if the camera shifted.
But anyway, you are not using the camera.
I have to change?
Yeah.
I forgot to change. So now I think I will try to use the camera a little bit. Yeah. So since the domain is not a point, so if you want to say f is a minimum, so let's consider some function f, and if the variable is a point is in a vector space, then to say that f has a minimum at some point x0, you need to vary the point and compare with the value of the function at nearby points. So how do you do that? So you move the point in some direction by a certain amount t, And so you compare with this, and then you calculate the variation of the values when you vary the point. So this gives you the local approximation. So this limit t tends to 0 plus will give you one directional, I mean the directional derivative in the direction h when you take the point x0. So this will give you the df of x0 in h. So this is the way to calculate the local derivative. And if you have a domain, how do you do the same thing? So instead of a fixed vector, you take a vector field, because now the points will vary when you change the shape of the domain. You take a nearby shape. Let's say this is the nearby shape, which means you perturb the boundary of the domain using a vector field. So you need to move the boundary by some vector field, let's say v of x, which you defined previously, and by a certain amount. So the t will be the magnitude, and if you take v, a vector of num1, then it just gives you the direction. So by applying this vector field to the domain, any point moves by fixed by this amount x plus pvx. Here in the transparency I have used theta. So this will so the image, so if you call this function phi t of x, then the image of the domain phi omega will be a new domain omega t with the new boundary. Okay, and the idea of using a smooth vector field is that if you have originally you have a smooth shape, then the new domain by this perturbation will also have a smooth boundary. And so if the original domain had some perimeter, the new domain you can also in principle calculate the perimeter or the volume of this domain. Okay. And so now you can define analogous to this the 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 variation of the function with respect to this uh, vector field or with respect to this perturbation. So you define the directional derivative at the point omega. Omega now is my point, is a domain in the direction of the vector field. This is a function now. Okay, is by definition the limit as t tends to 0 plus of j of phi t of omega minus j of omega divided by t, if this limit exists. So you do not know for sure that this limit always exists. It will depend on the function j. The same way that any function on the real line, this limit may not exist. It has to be differentiable. So this limit has to exist. You have to show if it exists or not. These are some questions which you need to analyze. But if this exists, then it allows you to calculate variations of the function with respect to variations of the domain. And in an analogy with respect to the Euclidean problem and the infinite dimensional problem, so there is a first order condition for a domain to be a local minimum. In this case, omega is a local minimum. If omega is a local minimum, then it's a necessary condition. Then this functional has to be 0 for all perturbations of the domain, for any perturbation by a smooth vector field. Okay. And you can also calculate higher order derivatives of this in a suitable way. And again, you can have a sufficient condition using the second order derivative. So You can define higher order derivatives of shape functions. So let me show what when you do this, what kind of um, derivatives you obtain for some typical class of functions. So one of them is of which interested us was the area of the domain in the problem of isoperimetric inequality, in the Dido problem. So the area of the domain is simply the integral on the domain of the constant function. Okay, this is my functional, and I want to know what is dA of omega for vector field theta which acts on the domain, the boundary of the domain. And the result in this case is it is a integral on the boundary, and it only depends on the normal component of the vector field, and you just need to integrate this. This is the result for the shape derivative of the area or volume functional. You can also do it in higher dimension. So it's not difficult if you use calculus 3 techniques. You just need to write. So what you need to calculate is a of omega t minus a of omega divided by t, and so this will be integral over omega t dx minus integral over omega. So for the area, it will be a of omega t minus a of omega and so you just make a change of variable. You know that the omega t is the image of omega under the phi t, the perturbation field. So if you make a change of variable, obviously you have d of phi t dx. The new variable you can put y omega because this is simply phi t of omega. And so if you change variable in this integral, x is phi t of y, then you just have this integral. And therefore, so this calculation reduces to the derivative of phi t, which is easy to calculate because phi t is the identity function plus t times the vector field or theta. So pt of x minus the identity in x will give you just t theta, and divided by t as t goes to 0 gives you theta. And so this gives you simply theta over omega dx. But you will say, why? How do you get this? I mean, not. There's a problem. I don't know what the problem. Yeah, there is a problem. Yeah. No, yeah, this is not, yeah, I have to calculate, I made a mistake in calculation. So d phi in this, it's the derivative with respect to the identity. And since the identity function, so its derivative is just the identity matrix. So this will be identity plus t times d theta. Okay, we are deriving with respect to x here in this d phi is the derivative of the vector field. So you have, in this case, at the end you have omega d theta dx, and now you just use divergence theorem of Gauss to say or integration by parts, and you get the integral on the boundary theta dot n. N is the normal vector at any point on the boundary. Okay, so what is the moral? So if you have a shape functional, and if the derivative exists, since the shape variation depends only on the variation of the boundary, and for varying the boundary, if you move the boundary tangentially, has virtually no effect on the boundary. Only the normal component will have an effect on changing the shape. So the moral is that in general you expect the shape function only to depend on the normal component of the vector field, and you should be able to write it as a boundary integral. Okay, so this is what one tries to do in any shape optimization problem. Okay, and so in the case of this area functional, you have this shape derivative, but remember that we are looking at maximizing the area with fixed perimeter in this problem, the original problem. And so we also need to take into consideration the constraint. It's a constraint problem. So you also have to look at the variation of the perimeter function.
Una consulta, que todas estas cosas ahí son cálculos locales, pero el
Sí.
problema inicial que planteaste es global.
Global.
¿A eso vas ahora?
No.
No.
No, the shape derivative technique usually can only help find local minimizers. It doesn't help in getting global.
But this is true for any derivative.
No, I know, but
Yeah.
the solutions that you are given are
Yeah.
local solutions, but
Yeah.
the problem that were posed at the beginning was global. That's why you're confused.
Yeah. But once you have some necessary and sufficient condition, so if you, in some cases, it will tell you the local solution is also in some sense global in
And
sense.
this will depend on the,
Yeah.
the conditions on the omega at.
Yeah.
There are still other issues, like if suppose that in A omega, we have integral omega over some function g of dx. Then if we do it for any theta, maybe that will not be the admissible domain.
Right.
So theta has a role here. Okay, for the time being, it's all.
So all this I've already said. So the definition of the shape derivative, and if it's shape differentiable, then it should be a function which only depends on the normal component of the vector field. And now we want to calculate some typical shape derivatives. So this is the first order condition for a local minimum or maximum. Yeah, so let me keep this on screen. Yeah, as Xavier pointed out, it won't tell you more than whether it's a local or maximum or minimum with these ideas. So you may need something more to say whether it's a global maximum or minimum. Usually the shape derivative technique in this sense is somewhat like restricted, but at least it helps you in problems which you don't have any idea how to do it, like theoretically prove some shape is a minimizer. You can test the shape with this idea. Okay, and And in problems like this imaging, inverse imaging, you do not know what the shape is. So it helps you at least you can give numerical algorithms to find local minimizer. So if you start from the initial shape, you can apply the gradient method like Newton method to start from and iteratively calculate actualizations of the shape, and it may converge to some uh, interesting shape which solves the problem locally at least. So obviously it's a defect. So it is not a it doesn't give you global solution. So, yeah, that has to be made clear. Yeah.
And very costly.
Question.
Huh?
A question about the same thing.
Yeah.
Do you usually have some sort of compactness or coercivity condition that tells you
Yeah.
that the optimum exists?
Yeah,
in
those
these
are
problems?
two different problems. So the existence problem is different from the characterization problem in some sense. So for existence, you need to use some compactness, as you said, and you have to define suitable notions of convergence of sets. So one example of convergence of set is when the Hausdorff convergence. So you can expand the shape by a small amount and or contract the shape by a small amount. So if the so two shapes are close when the expansion and contraction of these two are close to each other, meaning by some set inclusion. So and if the perimeters are finite or bounded, then you always have compactness. If you put a restriction on the perimeter is like not more than something, then for this convergence you can show that the class of competing sets is a relatively compact set. So it may have many limit points, but you can know that you can go along some subsequence and get to some solution using the convergence. And then you need the continuity or the lower semi-continuity of the function for having a minimum. Okay, so those are like complementary to this lecture. They are not part of this talk. So I'm just trying to focus on where it can help the shape derivative idea.
Oh,
And so now I said for the problem of isoperimetry, you need to calculate shape variations of the perimeter, which you write as integral of the boundary. Now this is the surface integral, and one approach to this is write the surface integral as a parametric surface, and write it as a domain integral, and then you can do the same thing as before using the parameterization. So I'm not probably going to give details of how you calculate the shape variations, but the idea is that given this domain, you may use a fixed domain D and then describe the omega, the boundary of omega, not omega, as a parametric surface. So this will be the boundary of omega. In this case, it will be the perimeter. And so the boundary of omega will be a parametric surface. And so when you make shape variations of omega, the boundary also changes parametrically by the change of variables. So you can keep track of the boundary also. Okay. And so the shape derivative at some point for some vector field again theta, which by definition will be this. if you calculate, then necessarily you will find that this is another boundary integral where you will have the curvature of the boundary as a component, and so I did this calculation for f equals 1, and then we already have the shape derivative, and for the volume it's what I showed, and for it's the same slide. And this is the proof which already I've spoken. Yeah. So imagine f is the constant 1, then you have the boundary of the domain. Gamma is the boundary, which now I write by gamma, or you can write delta omega. And so the gradient of the constant function is 1 is 0. So this disappears, and you have divergence, the tangential divergence of the vector field. And you have another Gauss theorem where you can use this, write it as another integral, and it will reduce to the curvature multiplied by the function f, which is 1, and theta dot n. So the component which appears here is the curvature of the boundary at any point, theta dot n. So this is the shape derivative for the perimeter function. Okay, but if you do it systematically using the parametrization, and then if you use the Jacobian for the change of variable, now it will be a Jacobian for the surface integral, not for the domain integral. Okay, so if you do everything carefully, then you will get to this result. You will first get to this result, and then using some differential geometry techniques, you can change this integral to this other integral. Okay. And so more or less, at least we can say for the problem of isoperimetric inequality, what the solution will be or has to be using these two derivatives. So the problem of the isoperimetric problem can be written as either you can do it either way. You can either minimize the perimeter fixing the volume, or maximize the area fixing the perimeter. In both cases, you have a constraint problem. So you have, for example, omega. This is the volume, and then you add the constraint using a Lagrange. What do you call a multiplier? So it's add a. So you have like lambda integral of omega. And so this you want to be a constant. So this is your multiplier, Lagrange multiplier for the, and I can put minus if you want, if it's more suitable. So when you minimize this, then this is your function j of omega. So dj by these calculations will be integral over omega for the vector field theta will be integral over omega theta dot Vn minus lambda, the curvature theta dot n, right? Because you derive this and derive this. It's a linear, the shape derivative also is linear for with respect to sums. Okay, so this you will have, and so the first order condition will say for all theta, this integral vanishes, which means for any perturbation, and so which means that since this is arbitrary, which means that 1 minus lambda kappa, the curvature has to be 0. Because if an integral, if you have a function such that for all test functions this is 0, then this implies the function itself is 0. And so 1 minus lambda kappa has to be 0, which means the curvature is constant. And so I think from that you're able to conclude, at least in the plane, that this has to be a circle if the local minimizers are circles. Okay, so this is probably to give a complete example for one situation, but if you want to look at the more physical problem of the drum, then you need to work harder. So all I'm saying here is all known and nothing is new. And this is just meant to be an introduction to how you can use this to study maybe interesting problems. So the idea is to work with the same kind of technique, but on a model problem which one might be interested, and which means you need to calculate shape derivatives and then study necessary sufficient conditions probably for some situation. I'm not giving here the second order derivative for these functions, but those can be found in the text. So actually there are like 2 or 3 books which are like very frequently used as references. One is by book by Sokolowski, and then there is a new book by Delfour and Solecio, where all these things are discussed in detail. So for other problems. So this is about the isoperimetric problem, and then you have now this is another class of problems. So the for example, this is not exactly the Rayleigh problem. For the Rayleigh problem, you need to consider an eigenvalue problem here. So actually, this is the second example. Yeah, so so the base frequency of the drum can be written as the minimum of some integral functional, some quotient of integral functionals. One is the energy of the vibration, and here it's some amplitude of the vibration. So this minimization has to be done first of all in some Sobolev space, and you need to know that this minimum exists. And actually it corresponds to an eigenvalue problem minus Laplacian u is lambda 1 u, where lambda 1 will be the first frequency of this domain, the base frequency. So then you need to calculate the shape variation of this domain and use the so the constraint here is that the drum, the area of the drum is fixed. So you will the constraint will include the area functional, but you also need to calculate the shape variation of this eigenvalue function. And without going into the details, one can show in fact some of these ideas are in the chapter 10 of the book, which I told del pure mezzo ratio. Shapes and geometries. So you can calculate the shape variation of this for perturbations of the domain. And this is actually minus the integral over the boundary. The normal derivative of the first eigenfunction to square theta dot n, where minus Laplacian u is lambda 1 u. So it's the vibrating mode, the u is the vibrating mode of the function, the form of the ground when for this vibration. And u is 0 on the boundary. So if you do the calculation, you can get to this. And one, actually, when you have a minimum of the functional omega itself, if j of omega itself is the minimum of some class of functions of this form, it's actually quite easy to calculate the shape derivative. You only need that f has to be suitably regular and some conditions on the class of minimum points for this. This minimization is with respect to u in some space or subspace. So if a certain class of conditions hold, then dj of omega, it's quite simply the boundary of omega f of x is the minimum of f of x u grad u theta dot n, where this minimum is taken over all the minimizers, so argmin of this original problem. So if the original problem has only one minimizer, like in the eigenvalue problem, there's only one eigenfunction corresponding to the base frequency, then you only need to calculate this. And in the case of the eigenvalue function, this is the gradient u square, and since u is 0 on the boundary, the tangential derivative will be 0, and so you only have the normal component. And so maybe there is something to do with the minus sign here, probably have to check, but more or less this is the this is more or less the shape derivative. So it's not hard to prove this when the shape function is a minimum of some other functional on some Hilbert or Banach space. Okay, and so if you now go back to the problem, then if you use again the Lagrange multiplier technique, it will say that you have minus Laplacian u. So this would mean that integral the normal derivative squared minus the constant, the Lagrange multiplier, and since it's the area function, the constant which multiplies is 1, theta dot n should be 0. This is the necessary condition for a minimum. And which means that the normal derivative has to be constant on the boundary. And so not only u satisfies this equation, but also the normal derivative has to be constant. This is an overdetermined problem, and there are not many domains for which you have a solution. The only domain for which this overdetermined problem has a solution is a ball. And for proving this, you need to use techniques from partial differential equations. It's not straightforward, but it's some classical result by Serrin in the 70s. So this is another way of proving. So the original proof of Haber and Kran does not use the shape derivative. They prove it in a different way using some other techniques from analysis, but this is another way of proving the same result. So you can always transform the problem. You expect to find some overdetermined problem and try to solve it either theoretically or numerically. So more or less, this is what I wanted to say. And so without this condition in int domain, you have a solution. But if you add this condition, because it's a minimum, then this becomes overdetermined, and this means that omega is a ball. So this is the only domain where you have a solution to this problem. And similarly, you can look at other problems where you can look at some other generalizations to these equations. So I don't want to get into those stuff. So thanks for your attention, and
Thanks, Rajesh. It was really interesting. Since this is the topic of my interest, I really liked it. So let's go for the questions.
Como en el problema original del video ahí tiene un semicírculo. ¿Se devuelve igualito? ¿Se devuelve igual o falta algo ahí para concluir? ¿Qué hiciste antes ahí para la...
Que ahí una parte de la frontera es como no tiene condición, solo tiene la frontera libre. La condición sería sobre la frontera libre que la curvatura es constante.
El aprendido construye al lado de algo, de un
Sí,
río,
sí.
de algo que le da
Sí,
un...
pero entonces tú lo que...
O lo puedes simetrizar, que puede convertir el mismo problema que varias.
Ah, sí, se puede simetrizar ya.
Sí.
O sea, pero para el caso específico,
Sí.
for the special case, sorry,
Sí.
for the special case that it's 100%.
Sí.
When that is just
Entonces,
fine.
resolviendo el problema
Ya, ya.
simetrizado, puede obtener solución para el problema del mitad del dominio también, que son
Y si no, existen resultados como de relativos cuando varías el omega at, por ejemplo. Entonces la J está fija, está todo fijo, y you modify the admissible conditions. So there exists some kind of relative results, like if you can do it for this family, then you can do it also for that one, stuff like that.
I think it's a good question, and I think it must have been used, this idea, I mean, in some problems, but I don't know exactly what problem you can, like, when it doesn't come to
And
my
it's some
mind.
sort of
Right.
equicontinuity thing, like taking the isoperimetric problem and shifting the perimeter continuously, and then you shift the circle continuously as well.
Yeah.
So that in more general cases.
Or even you can say, maybe you can approximately solve. So if you know for the class of smooth domains, then you can ask what is the solution
I was thinking more of this kind of...
for polygonal domains. And
Yes, I was thinking more.
yeah, you can do like use perturbation argument to, if you solve for this class of domain, then you may imply
Because I
some.
was wondering, because at the beginning you say
Yeah.
if it's very irregular.
Yeah.
But it shouldn't be. I mean, if you have this kind of relative results, I mean,
Yeah.
some square results, then maybe even very irregular shouldn't matter so much.
Yeah, certainly, yes.
Any more questions? Comments? Nance, do you have any question? Can you listen to us?
No, I have a friend from India.
There are many people there, actually. No?
I don't know if he's there hearing.
You have to stand there. And ask if he has.
Nance, do you have any questions? You have any questions? People there connected?
No, no question for me. Thanks a lot.
Sorry, yeah. Okay, so let's stop here then.
Okay.
Thank you, Rajesh. Thanks a lot.